Assalamu alaikum everybody to the second part of lecture number 5 about antenna arrays. In the first part we talked about linear antenna arrays where we have the antenna elements arranged in a line, and we talked that linear arrays are one-dimensional arrays that can scan the beam only in one plane. For example, if we have the antenna elements arranged on the z-axis, we can scan only in the theta, like elevation plane. We can't have any scanning on the phi or azimuthal plane. To scan the beam in any direction, which is like elevation and azimuthal, we need two-dimensional arrays. Two-dimensional arrays are arrangement that are in 2D, like in a circle, in a planar, on a cylinder, so on and so forth. And this will be the focus of this second part of the lecture. Here we have this like example of an arrangement that's like 2D. We have the antenna elements arranged in the XY plane. We have M rows parallel to the y-axis, like so. The dimension in x is m, the dimension in y is n, and we have the antenna element arranged this way. And we would like to study this geometry or this arrangement so that we can come up with the array factor. This is what we are focusing on when we are dealing with antenna array analysis. So the array factor, like for the elements on X, are like M and M1, like 1, 1, 2, 1, 3, 1, so on and so forth, and we have M elements. So here actually we are talking about the first line along x-axis, so y equal 1, which is fixed, M is varying, so we are talking about here 1, 1, 2, 1, 3, 1, 4, 1, up to M1. So we are talking about the array factor for just for this column. Okay, so for the column, which is the array arranged along the x-axis, for column number 1, so 1 is the y index, M is the x index is from 1 to M, as shown here, from 1 to M. So we are talking about this column here. So the array factor is the amplitude. Then we have like the phase, if it's like linear phase, similar to what we did with a 1D antenna array, it would have this expression. So this is linear for one column. If we are taking all the columns, this is what we do. So we assume this whole column is an element, because like this array, linear array, or this column is acting as like an element, and we are repeating this element over and over again. So the array in the Y can be thought of as an array of columns. So we have this expression. So we have the column number 1, then we have column number 2, column number 3, column number 4, so on and so forth, and up to column number n. The difference from column to column is dy and a phase shift from one element to the other. So if we are moving here, this is phase 0. The phase here would be phase 0 plus beta x plus 2 beta x plus 3 beta x. If we go here, it will be 3 beta x plus beta y, 3 beta x plus 2 beta y. Here it's 1 beta x plus 2 beta y. Here 1 beta x plus 4 beta y, so on and so forth. So every element we have beta x, successive increase in phase along the x direction, beta y, successive increase in phase in y direction. So if we are now like talking to the planar, So from each element we have, from each column we have the array factor along X. Then those columns are arranged along Y. So we have this factor or like this summation along Y. So just give yourself like some time to understand the math. You will find that the array factor for the planar array is the array factor along X multiplied by the array factor along Y. So because we have like 2D array, we have like two summations, like 2D summations. In this case, when we have like non-uniform planar array, but the phase from one element to the other is increasing by a constant rate, by and bx. The pattern of this rectangular array is the production of the array factor along X by the array factor along Y. If we have any difference, for example, like the distance are not of the array, they are not uniformly spaced, or they are not uniformly like increased in phase, we just go to the general case and we just substitute or like use the more general formula. This formula is, as I said, is used when we have like uniform distribution. dy is constant between one element to the other, dx is successively increasing from one element to the other, same as beta x and beta y. So this is linear phase increment from one element to the other. If we have a different situation, we go back to the more basic summation of terms. So we go back to a more basic case, and we do our math for the new setup if we have a different setup. So in this case, like when we have, like for example, now we'll talk about applications. If we have a uniform array, uniform means beta x equal beta y equal 0, and we have like arranged like in a regular way, regular arrangement. So the separation from one element to the other along x direction is dx, along y direction is dy. We'll have the psi x does have this expression, psi y does have this expression, m is the number of elements along x, n is the number of elements along y. Again, it's very similar to 1D array along x, 1D array along y multiplied by one another, and this is normalized. So we divide the first array factor, the x array factor, by m, the y array factor by n. So this normalized array factor in this case does have a maximum of unity. Again, this is general, like beta x and beta y can be like 0 in this case, as the title is suggesting, but this expression, if beta x and beta y are non-zeros, it will be like valid one. So this is general, but if we want to have like a uniform array, beta x and beta y will equal 0. Uniform means everything is fed with the same magnitude and same phase, and this is the case. They said like uniform array or equal amplitude and phase excitation if the number equal 5, so 5 by 5 array, the separation is lambda by 2, we would have something like that. So just to have a feeling. And if we have beta x and beta y non-zero, we can have like the array is scanned along, like the peak is going at phi equal 45, theta equal 30, and this would be the shape of the 3D antenna pattern, or like array factor pattern, sorry, when m and n equal 5 under those conditions, just to have a feeling. And you can notice easily that the shape of the main beam is different between the two cases. and this is very expected. When we go off the peak, the main beam will also like change its shape, not just the direction. Its direction and shape will be changing. Okay, as we did with a single dimensional array, we would like to study the position of the maximum, the position of the nulls, so on and so forth. So the maximum for phi x, the maximum for the array factor along x, is the maximum of this sinc function, and we did this before. This is happening when psi equal plus minus 2m, where m is an integer, by where m is 0, 1, 2, so on and so forth. In this case, this is the expression for a peak coming from this x array factor. Similar condition for a peak coming from the y array factor, and this is happening for m equals 0, 1, 2, n equals 0, 1, 2. So the first main maxima will be when m equals 0 and n equals 0, and this will like drive the peak of the array for a certain theta and certain phi. So theta naught is the direction in theta of the peak, phi is its direction of the main peak, the first one, 0 and 0. So we just like write down the expression. We find that for the first peak of the x part of the array factor, we need beta x to have this expression. For the first peak coming from the y array factor, this is the condition for y. So, and this is bringing the peak at theta naught and phi naught. We need to find those. So just solving those problems simultaneously. So we can divide the first one by the second one. It will give us tan. So if we divide b by a, we'll have tan phi naught equal beta y dx divided by beta x dy, and we can find phi naught. Once we found phi naught, we just substitute in a or b to find theta naught, because this is known, this is known, this is known. Once we know phi naught, then it's just like two linear equations solved simultaneously. We can have like this closed form expression, which I don't recommend people to memorize. So we have two equations, we can solve them simultaneously. I'm sure that you can do this easily. So this is a way to find the direction of the first maximum. Also, it's very straightforward to solve the reverse problem. It's very common. I ask you, okay, design the antenna array so that the first peak would be in this direction. Design means you choose dx, dy, beta x, beta y, so that you have the peak in theta 1 and phi 1. So this is like very regular kind of like design problem. Another type of 2D array is a circular array. The circular array, as its name suggests, is arranged in this shape. So we have the antenna elements arranged in a circle, let us say in the XY plane, and this arrangement gives us the ability to scan along theta as well as phi. So look here for the geometry, because again we will exercise deriving the expression for the array factor and studying, means or analyzing the circular array. Why the circular array is useful? because again it's 2D, so it has the ability to like scan in any direction. One very regular or like good property of circular array is that because it is like uniform in phi, the pattern even when we are scanning also will be uniform in phi, which means if we are changing phi, we'll have the same radiation pattern. If we are for fixed theta, if we are like rearranging or like feeding the antenna to scan along phi, it will be same shape because of the symmetry. And it has applications like smart antenna, radio direction finding, so on and so forth. So it has its own application as well as the rectangular 2D antenna array. So as I said, you can scan beam in any direction. It provides elevation and 360 azimuth. You can like scan it for any direction in phi. There is azimuthal symmetry because like the arrangement is symmetric in phi, so its behavior or the antenna array pattern is symmetric in phi as well. One thing here, like the elements are continuous. Continuous means that you can say like in linear you have a start and end, but here because it's circular, it's sort of like it acts as it's long, and this will result in low side loops because it looks like it's continuous. So it's as if you are bringing like an linear antenna array and like curve it and make a circle out of it. This will reduce the side loops. It can also like utilize basic phasing techniques like phase difference from one element to the other, and something related to like reduced coupling effect. And by the end of this part of the lecture, we'll talk about the coupling effect or the mutual impedance effect. So back to our arrangement. The antenna elements are arranged in a circle. This is 1, 2, so on and so forth. We have n elements arranged on a circle, and of course you can calculate the angular space between one element to the other. It's 2 pi divided by n, and as an approximation, we are assuming that the vector going from any element to the observation point are parallel to the vector going from the origin to the observation point. And we are using those approximation for phase. The r, the distance from element to observation point, equal r, which is from origin to observation point plus minus delta r. For example, like this element, it has Rn, which equal r from origin to the element minus this delta. And from the geometry, you can see this is a right angle triangle. So this is 90. This length here is constant, which is a, the radius of the circular array. And we are interested in this distance, and this distance is a cosine this angle. So this angle psi n is the angle between the direction of observation AR and the radial vector to element n. So if this is element n, so this is the radial vector to element n. And I'm expecting that all of you know how to find this expression. And we're going to do this in the next slide. But I'm expecting that you can think about like a very systematic way to find A is constant. So we are talking about cosine psi n. And for amplitude terms in the array factor, we have Rn. We take it as an approximated to R from origin. So our array factor, normalized array factor, which means that the array factor, or like, sorry, the normalized, here they are talking about the normalized field, which is the array factor, assuming that the element is a unit isotropic element. So all the field is coming from the array factor. So here for the phase we are using Rn, which is like this expression as we saw in the previous geometric slide. And for the amplitude term we are using Rn approximately equal R. So here for this expression we are interested in finding a systematic way to find cosine ipsi n. So cosine the angle is the dot product between the two vectors that are making those angles. And as we defined ipsi n in the previous slide, it is the angle between the direction of observation and the radial vector to element number n. So again, from this arrangement you can find, or you can express this vector in Cartesian. You can express this vector also in Cartesian and do the dot product. So the first one, a rho n, it is in xy plane, so it has x component and y component. I'm assuming that everybody can do this, write down this expression. This is the expression for a rho n, this unit vector, or the unit vector in that direction. AR, which is the unit vector along the direction of observation. And again, like we did this before a couple of times in microwave engineering as well as in this antenna course. And so just write it down, do the dots product, and you will find the expression for a cosine ipsi n, which does have this expression. So now Rn equal R minus this expression, and we're going to substitute this only in the phase term, while the amplitude term we are using R equal R small. So the normalized field, this is the definition as I said in the previous slide. We are just doing this. For the amplitude term we are using R. For the phase term we are using R minus the expression here, which is a sine theta cosine difference. A sine theta cosine difference is now here, and we can now write down the normalized field expression. This is like from origin, and this is the array factor for the circular array. So all what we need to do is now like just run this summation from 1 to n. We can call this psi. This is another psi different than the ones that we see here. So now this is the psi of the array factor. And we call this phi n, which is the phase. Like now phase from element to element is increased by certain amount. So this is the phase difference of element number n. So the feeding factor to element number n, again phi n, here as I said it's 2 pi divided by n. This is the angular position of element multiplied by n. So first element is at 1, second element is at 2, so on and so forth, based on the arrangement that we have here. So element 1 is 2 pi divided by n, So this is number 1, then you double this for number 2, so on and so forth, to arrange n element on a circle in the xy plane. So to steer the beam to the direction theta naught and phi naught, if you want to like arrange this antenna array so that we have the beak along theta naught and phi naught, we need the psi to equal 0 in this direction. So when we put theta equal theta naught, phi equal phi naught, we need alpha n to equal the negative of that. So this is the condition. This is the condition for steering the circular array factor along theta naught and phi naught. So the beak would be in that direction. You can just like review the math and you will find out this condition. So the array factor, again here, it's just like writing it in like more detailed way. And here is the normalized one where we divide by n, because this is the maximum of this expression. A special case of circular array, again, now circular array, any kind of arrangement, I think we now should understand the basic, and all of this is just sort of like an application. When it's a uniform array, which means that all the antenna elements are fed by the same amount, by the same phase, so you will have this expression. The expression does have a Bessel function, so on, so forth. You can like read those slides. I don't want you to memorize or like handle like a special case. If we are to deal with a circular array more frequently, this would be of an interest to us. But the main idea here is to understand how to formulate the problem and reach the like analysis that you want. Again here, this is sort of like putting rules and names for uniform circular array. Again, this is for your information. If we need to drive this, we can just go to the basic expression and drive it. And here we have like one case for uniform circular array with n equal 10, so on and so forth, just to have a feeling for how the pattern, the array factor pattern would look like. And here this is like a 2D version of it. So this is for one plane is the solid lines and another plane the dotted lines. So one last item for this topic is self and mutual impedance. All what we studied so far assumed that the antenna is isolated or nothing is next to the antenna. But in reality, especially in the case of antenna arrays, we have other objects, in other words, other antenna elements next to the antenna, and those antenna elements affect the behavior of the antenna. This effect is called like mutual coupling between antennas or mutual impedance between antennas. So studying or understanding this terminology is important, and its importance is higher when we are dealing with antenna arrays. So for example, if we have like this antenna number 1, like fed by certain current I1, we already studied this case, so we can handle this. And when we do the analysis for this part only, we are talking about isolated antenna. So this antenna is radiating field. At this position, if we have another element another antenna, the field at this position is E2 caused by element number 1. So the field generated by current 1 on antenna 1 at this position is named E21. This field, when it imping on the antenna, or when it's incident on the antenna, it will cause some open circuit voltage on this antenna, and this will push some current I2 on this antenna. This current will radiate, and its radiation will come to antenna 1, cause some changes, and this is called the coupling, or the mutual coupling between the two antennas. So this is the idea of mutual coupling between antennas. So when we have antenna 1 radiating, antenna 2 is non-energized, there will be some voltage induced on 2 because of the current on 1. This voltage, open circuit voltage, does have a value. If we divide this value by the current caused this voltage, it will be the mutual impedance 2-1, the mutual impedance of element 2 because of the current on element number 1. If we have the two antennas energized at the same time, so the potential or the voltage on antenna 1 is Z11 multiplied by I1 plus Z12 multiplied by I2. So the current 2 will cause some or induce some voltage on antenna 1, and the self impedance, or Z11, is called the self impedance of antenna 1. So the self impedance approximately equals the input impedance of the isolated antenna, of the antenna when it is next to nothing, when it is by itself. So this is the expression when we have two antennas. If we have three antennas, we'll add more terms of mutual coupling, but as you would expect, if we have another antenna here, the coupling between 1 and 3 will be weaker than the coupling between 1 and 2, so that we can neglect the coupling to the next element. So just keep coupling to one element to the right, one element to the left, or just the nearby antennas, not to go for the second row. And one thing here from reciprocity, we talked about reciprocity theorem, Z21 equals Z12. How to find this, like open circuit 2-1. So open circuit 2-1 is caused by current 1 when at antenna 2. So we go for antenna 2, we use the field generated by 1 at the position of antenna 2, and we like have a dot product of this. So anyway, with some like derivation depending on the reciprocity theorem, we can find out that the open circuit at antenna number 2, because of the current on antenna number 1, does have this expression where we divide by I2, which is the input current which is I2 of 0. And if we are looking for Z21, it will have this expression divided by I1, which does have this formula. And in a similar way, if we are looking for the self-impedance would have this expression. So anyway, this section about mutual impedance is like, again, is important part for the design and the implementation of antenna array, and those are sort of like the summary of needed expressions and definitions for this part. If we needed to go deeper into this, I think now you have the entry point that you can use to dig deeper into the topic. Thanks everybody, and hope like we'll have, inshallah, we'll have a discussion on Tuesday about this part of the lecture. Assalamu alaikum.